Hello children, this is Sanjay Kumar Varshney from Center for Nanosoftware Sciences, Bangalore North. I'll give you the glimpses of fourth stage of matter. As you might be heard, fourth state of the matter. What is the fourth state of the matter? Now you can see here. You know that solid states in which molecules are arranged in three-dimensional positional order, orientation order, but there is no flow and there is no show the bifurcations. Where in the case of liquid and gases, no positional order, no orientation order, no flow, and no bifurcation. Their molecules are free to take the shape of the container. But in the states, here you can see these molecules are between the two states, either liquid or solid. Now you can see here more clearly the solid states in the molecule are arranged perfectly in positional and orientation order. When the case of gases or liquids, molecule are free to rotate. But in the case of the fourth state of matter, which we call now liquid crystalline phase, in which the molecules are arranged in 1D, one-dimensional or two-dimensional order, has the little bit fluidity and birefringence. So this in this molecule are little bit free compared to the solid, but is restricted to the liquid. You see here molecular packing. What the molecular packing of this type fourth system matter is happening. So here I will show you. You can see here these two types of molecules here. One is the circular, looks like this. One looks like is rectangular. So in this circular, what happened? Two benzene ring, two benzene ring are connected with the covalent bonding, where in this biphenyl ring which connected the covalent bond and have the circular form. I will explain this in the next slide. So what the advantage in this two? One, this molecule has one dimensional molecular structure, as you can see here, and they have two dimensional charge transportation facilities, which shows the symmetric phase or layer structures. So here you can charge transport in two directions, z and bi, where in this type shape molecules charge transport in one direction, you can see. But the two molecular structures which form the Columnar phases or layer structure. In this type molecules, I will explain at a talk on this type molecules. This type molecule you can see in this molecular pattern like this. You can see here this is the gray area is called the conducting core, was nothing but the benzene type molecular structure, and there's a space between these two. You can see the whitish area which is called the aliphatic areas, in this which rings are is connected separately. So between these two rings, this is approved by the XRDs. The core distance, which is from the one core to another core, is about 2 to 4 nanometers, where the core separation between two discs, which is about 0.3 to 0.4 nanometers, is reduced. And this aliphatic chains which work as a insulating chains, and due to this core aliphatic chains which connect to the core is from the mesophases. So in these molecules we are using the charge transport from the up and down. Towards up as work as the molecular wires, electron charge transfer wires. See here now. So again here I can classify this liquid crystalline in two types. One is a thermotropic, one is a lyotropic. So we will discuss here only the thermotropic part. Thermotropic liquid crystal. Where is this lyotropic? In this nothing but is the mesophase formed by the solvent and concentration of the solute. So here two liquids are formed, in which is the electrons donor and one electron gainer. So they form the head and tail combination and form the molecular phase. But in this case, in thermotropic liquid crystals, a mesophase formed either in the room temperature or on the little bit giving the thermal energy, nothing but we giving the temperature. So in this like solid state, if you give small thermal energy, molecule come the liquid state, and then if you further heat it, it goes the liquid states. And when you remove the thermal energy, again the higher molecules come to the liquid state and goes to the solid states. Is a vice versa process. Now, the application of this type molecules as self-assembly of liquid crystal. You can see plenty of molecules here, like self-organized soft materials, discotics, like they are lyotropic molecules. The shapes in the liquid crystal, there is now more than two types shapes are defined, like spheres, rods, disc, and amplifiers. Amplifiers is used for the formation of the polymers, like you can see blastomers, polymers, side chain polymers, all the things, and DNA, which is work as a lyotropic liquid crystal drug deliveries. So and these type molecules also form the like climatic liquid crystals, whereas the discotics form the pneumatic and the columnar phase. These two is a forms where in the case of columnar, which is the type of molecules, shows the symmetric and pneumatic phases. See, now we will discuss here only the discotic shape molecules in which the central core is a more than one ring, one benzene ring, or less than one benzene ring. So this you can see here, which we call the polycondensed aromatic cores. In benzene was invented in 1888, and then this all product is a byproduct of the butyl products. So we can get the naphthalene, pyrrolene, pyrrolene, anthraquinones, and then come to triphenylenes, dibenzochyricine, and hexabenzocorine. And now recently might be heard now C16 fluorine, C70 fluorine, graphene sheet. Now is Nobel Prize is given. So you can see nanotubes, which is nothing but is the folding of the graphene sheet. So and these all molecules, what will form here? You can see there is no aliphatic chains connected. So this is the hard cores. So they have the core mobility, and see this forms the packing on that. So these molecules can be used in plenty of applications. First of all, your electronic gadgets, which are using the mobiles, touch screen mobiles, smart TVs, all the things. And nowadays they are using the nanotechnologies, medicines, flat panel displays, batteries, microphone, uh, paint industry. Nowadays they are using very much. So here we can say chemistry is our life or our future. So chemistry is nothing but each the bonding and non-bonding systems. So we can define as attraction and negative are basically two bonding systems. Now come to the work which I give you my glimpses, small glimpses of my recent works. So this is nothing but is a dibenzochyrine. Dibenzochyricine is a molecule in which has a small unique identity from this position, that this part and this part is the twisting like that. So you might be heard the helix, single type helix or double helix. So in double helix there is a left-handed or maybe right-handed, but a single helix also is left-handed or right-handed. So this type molecule can be used for any type of a purpose, especially for the by charge transfer properties. So I give you small examples here again. So these molecules, when you see under the uh, polarizing optical microscope, when the temperature is little higher, we heat the molecules, you can see this columnar phase has the bifurcations and has the patterning. You can see these knobs, and then this bifurcation, again this focal cones, and this is the columnar phase which is stabilized with the XRDs. This is again columnar hexagonal phase, and this is again columnar rectangular phase. In this columnar rectangular phase, the molecules four columns are formed as a rectangles, where in this hexagonal phase, same six columns are formed in hexagonal shapes. That's why we call the hexagonal and rectangular. You can see the difference between these two textures. So here is the forms of the rectangular. Now this molecule, when we do the computation studies or simulation studies by the simple camera or 2D energy mechanism structure, you can see this looks like it's a flat molecule. So here I remove the aliphatic parts to come to see the structure carefully. So when you see from the top of the microscope, it looks like flat. What as soon as you rotate around 45-degree your vision, you can see two pillar, popular and a single lobe. So this is nothing but is a looks like is a Y shape. But when you see again 45-degree rotate from the angle, you can see two cross. So this but nothing but is a two cross. So it's like this. So this shows that this molecule is not flat. So now this we confirm by the quantum chemical calculations. In this quantum calculation is again is a theoretical, which we use the Gaussian softwares to get that. You can see the stable state in the plus energy is cross, in which 22 joule per mole energy will give is. When go to transition state, you can see here it form the again by shape which give you the 41 kilojoule per mole energy. What same thing when you come to the achiral metastable. Achiral means it's nothing but is a flat. You can see here this energy is again just 22 kilojoule per mole. When you again go to the negative state, go to the by state, transition state, again energy is negative, which is 41 kilojoule per mole. Come to again stable energy, which is metastable, again the stable state, which is give you again the energy is this 22 kilojoule per mole. But if this molecule is flat, if you see here flat conformation of the molecule is supposed to be energy is 127 kilojoule per mole. This shows that compared to this energy and compared to this energy, this shows the molecule is not flat and has a transformation state. So now you can, which we have to confirm. How to confirm this molecule is not flat? We have taken the chirality in the ECD spectra. ECD spectra, in which you can see the quantum calculations. When you pass the circular diaphragm beam to a sample which is sandwiched between the two quartz plate, and you can see easily 10 nanometers, and then goes to then this will generate the quantum effects, which shows that this is a positive sign and this is the negative sign. When you start cooling, heating the sample, it goes to the positive state. When you start giving the energy, it goes to negative state. Means when you rotating when the sample is rotating 40 degree, 45 degree, and then again going to rotate. So here this experiment is quite tricky, which we did it. And in this we have to rotate the sample and close other parts of the area, so which we open the sample which covered with the aluminum foil, and on a small just 1 micron hole we pass on that beam is passed through the beam. So you can get this. That's why we are able to get the from 0 to 90 degree, again rotation 90 degree, and then you can get the birefringence, which confirm that molecule is showing the chirality. So now this molecule we want to show the electro-optical switching. So electro-optical switching means when we give the some current to a molecule, it will go on the other states. So or when we release the voltage, it should come on the relaxation state. So here you can see two lines here, green, red, and blue and black. So here when we give the 60, we have to fix the current is 60 volts of 10 hertz, but we vary here the temperature. So you can see this peaks when 60 degrees giving on at 60 degree peaks is smaller compared to this vibration is smaller, signal is small. When we go to the 140 degree or 100 degree, the peaks are gone up. This shows molecule has electrical switching. So in this POM you can see easily image. This you can see lighter space in this area when the current is 0, but when we current is not 0, you can see this brighter area, but when the current is equivalent to 0, you can see the dark area. So this shows that this molecule has the electro-optical switching property, in which we can give the, if we give the current of this molecule will go to flip-flop states. So for the best example I will show you here. Next slide. See here, this is a very good example here, in which Indian Railway are using now this smart windows, in which we not required any curtain or something, in which we can give the current. When switching on the switch, you can get the molecule is in off state. When you switch on the current, molecule is in off state. So you can see the visibility or similar like that. So other examples of the same thing we can see recently LEDs in the light emitting diodes in the fabrics and fibers, which is very important nowadays, coming soon in the market. You can see the fiber the LEDs, we paint OLEDs, we can see the TVs, all the thing. In OLEDs, you can see how the molecules just give in small current conducting surface and get the fiber. But in the case of fabric, means between the weaving of the two threads, we are giving some material and which will glow it. So you can see here the glowing like this. So these molecules are very interesting and can be used for nowadays for all the electronics purpose, especially energy storage, display devices, smart windows, which the coming, you can see the commercialization of the thing is quite interesting. And especially when I shown that the molecule which is the unique in itself in the non-chiral molecule showing the chirality in the columnar phase. So what you take away? Organic materials exhibit the fourth state of matter on which prominently used in advanced electronic devices, energy storage, flat panel display, sensor advantage. They are environment friendly and they can easily decompose. So advantage of this molecule, this is organic. You know that organic. Now you are hardening the organic foods, all the things. What happen advantage is that they can easily mix with the nature. Also, they are not giving the impact on the environment. Similarly, it is same like that. So advantage of that. So you can see this very simple. I will give you a small mobile phone consists of the number of layers. You can see the form start from the battery, motherboards, another layer, display layer, and then touch panels here. So these are the consists of the layers which consist of your mobile handset. So this is the top, which is give you the display device, and this is the biosensors which you take the current from your finger and transfer to the memory chips. And see again here, so what is that one? This is a touch screen, again display. So n number of things are, but still we are using very minute ppm level of lanthanides. You can see here which we are using now, nickel, gallium and tantalize for the purpose of that. But we want to remove this galliums, as you might be heard in the LED lights, which is not good for the environment. So all their rare earth which is not good for the environment. So we have to replace this soon, and you can see all this molecule to replace with the organic materials. Thank you.